All right, I see we're starting to have some people come in. So this is from last time. I'm gonna erase this real quick and then we can get started. Better eraser than stock. So I saw in the group chat that y'all are wanting me to cover limits, stuff like that, continuity, and that is what we will be covering today. Okay, so first I'm going to start out by drawing a visual representation of some limits. So we'll start with the most basic graph of a limit that I can find, and it'll just be a plain limit. We can say either the identity limit or the limit of a constant. Both should be quite doable. All right, so first rule that we're going to be working on today, let me turn some lights on. It is very dark in here. So first thing we'll do today then will be the limit of a constant. So if we've got the limit for a as x approaches c, where a is a constant, then the limit is equal to a, which is our constant value. So for example, if we had limit as x approaches 2 for some number 5, then the limit, the answer is just going to be 5. And there's a couple ways you can interpret this. I think graphically would be the easiest to understand. So if we draw out a graph here like this, where we've got our number c to which x is approaching, and our constant a. So then a, the function of a is just going to be a straight line because the rate of change for a constant is 0 because it's always going to be the same. It's just a straight line, just something to keep in mind. So then I'm sure you guys have seen Professor Kang do something along the lines of this. And we'll label this line right here as f of x equals a. So as you can tell, there isn't really a limit here because it's just going to be whatever a is. The limit, I'm trying to think of a way that I can describe this to you guys. The best way to think about a limit is as a pair of coordinates. So you can think of limit as x approaches some number, right? And then we've got some function f of x. So you can view x approaching some number as our x value, and then whatever that number is when plugged into f of x would be considered our y value. So we could call this like our x coordinate and our y coordinate. Just to put it into something simple, like the identity function, for instance, we'd have limit as x approaches, I'll say 4 for the function x. So the answer here is just going to be 4. And this is representation, a limit representation for the function y equals x, otherwise denoted as f of x equals x, which is just called the identity function. You guys should know that it's just a diagonal line that goes through the origin. It's a positive slope, obviously because there's no negative sign in front of it. So as you can see, this right here is the function x. Our x value that we're looking at is going to be 4 because it's a limit. So then when we plug 4 into x, which is our function, because this is y, so we need y in terms of x to represent y graphically in 2 dimensions. So then it would just be 4. So this could be like 4, 4, I don't know, something like that, right? Is anyone here having a hard time following this? I know this is very basic concepts. I just kind of want to give a general rundown of what a limit should look like. I'll give you guys a little bit of time here to just, if you have any questions, you can type them in the group chat or YouTube, whatever you want. I'll keep an eye on both for just, I'll give it about 20 seconds to ask questions here. All right. So I guess there are no questions to be asked, so I'll go into the next topic, which is just going to be our basic operations of limits. So this is a very just mathematical way to kind of look at this right now, because since you guys can't really be in class, visual representations might be a little bit more difficult to understand on your own. So I'm going to write out some rules of math for y'all, just so you kind of know what you can do and what you can't do. Because I imagine that most of you never have taken this class before, or some of you I'm sure took it in high school, like AP credits, or just didn't take the AP test, et cetera, but it's a lot easier to learn these concepts when you're being taught it in person. So I'm going to write out the rules because I know that a lot of professors don't really put the rules out in plain black and white, ones and zeros. So I'm just going to make sure there is no problems with clarification here and show you guys the basic rules of limits before we even attempt to solve some problems. So this one right here is the limit of a sum of 2 functions. So we've got limit as x approaches c for the function f of x plus g of x. So the way that this is broken down, and this is the only way to interpret this, you would have to write this out as the limit as x approaches c for the function f of x plus limit as x approaches c for the function g of x. So we can tell that, what would that be? Is that bound by addition? You guys don't need to know that quite yet. When you get into, if you want to know what these types of rules are called, you can ask Professor Kang in class, but because we did something very similar when I took his linear algebra class like last semester. It was just, when you get into vectors and scalars in linear, some of you will look back on this and go, oh, hey, I remember that. But for now, let's focus on calculus. So this is the same rule, by the way, with addition and subtraction. So plus or minus, it's not going to affect it that much, essentially. You just need to know that you can't just plug it in, like you need to separate them and plug the limit in for each function. And then let's see what else we've got here. So I know you guys also mentioned continuity, but I'm going to finish up the rules of limits here, just in case, just for my own sheer entertainment. Limit as x approaches c, and I'm also going to get into continuity at the end of this section. At the end of this section, don't worry. I'll spend half on limits and half on continuity, just make sure that everyone is good to go on everything. I really want you guys to understand these concepts because they really do build on each other. I know it may not seem like it, but you can think of this section as like learning to add before learning algebra. These are the building blocks of what you're about to be doing. So the next thing we have is the limit of a product, which is going to be limit as x approaches c for the function f of x times the function g of x. So that would be written as limit x approaches c f of x times the limit as x approaches c g of x. And as you can tell, these are very basic rules. Like you were probably taught something similar to this when you were first taught how to add like terms and stuff like that. They were just basically all these rules are telling you is that yes, this is still math, it's still addition and subtraction. You just have to separate out things, just like with having like terms. So we really need to be treating these in this manner, otherwise you will have a very hard time getting correct answers. So the next one would be the limit of a quotient. Or no, this is actually more important. We're going to start with this one and then get to limit of a quotient. So I'll label these, by the way. We'll say multi and then add / subtract. So the next one is going to be the limit of a constant times a function. And this is very, very important. This is like, as far as limits go, this is a very good rule of thumb to have in your head because this is a mathematical, like this is a rule essentially in almost any branch of mathematics you'll find or in every class you'll take for the next year or two, unless you're a math major. This is how it's going to go. It's going to be like, I'll stop talking and start showing. So limit as x approaches c for k, which is that we will call our constant term, times the function g of x is equal to the constant k times the limit as x approaches c for g of x, which essentially means that we're just taking the constant outside of the limit and putting it out front. So this is a pretty simple concept, but it's going to carry a lot of weight in later mathematics courses. Like once we start really diving into derivatives, this is going to be the same rule there. Derivatives follow the same rules as limits, and so do integrals, except integrals you can do a few more little interesting things with them, but you guys don't have to worry about that unless you're planning on taking Calc 2. So let's see, limit of a quotient. That's a constant times a limit, so we'll just say k times lim. I'm just trying to keep it shorthand, so I write very slowly and I don't want to waste your time. So limit as x approaches c for the function f of x over g of x is equal to the limit as x approaches c for f of x over the limit as x approaches c for g of x. All right, I'm going to check the group chat real quick, see if anyone has asked any questions. I'm going to go out on a limb here and say it's probably so early on in the semester you guys are still trying to figure out which questions to ask or how to word them. I know that I had that problem in Calc 1 a lot, but do not be afraid to ask questions. I'm very good at interpreting stuff. Like, I'll be able to figure out what your question is even if you can't word it the way you would like to. I mean, I would really like to help as many people with questions. It can be like if you give me a homework problem, I can work out the first few steps, but I cannot answer it for you. Just, make sure to utilize like SI as a whole as a good resource. It's a very good resource because I'll I'll cover whatever you guys tell me to cover. I'm just working through the basic notes right now. And once we get through that, I'll start working some problems. But I just have a feeling that a lot of you are probably going to have a hard time understanding these concepts at first, which is why we're going nice and slow. So let's see, is purple a good color? Green was the one that was hard to see, I think. Okay, so we've got, next one, we're going to have limit as x approaches c for the function f of x to the power, to some power, exponential power n. And that can be any number, it's just a constant, right? So this is equivalent to limit as x approaches c for f of x all raised to the nth power. And that's the power rule of limits right there. Power rule of derivatives is a little more interesting, but you need to know the limits first. And that's the same, by the way, like if you have to a fractional exponent, like it doesn't matter. If this was, real quick, if this was limit as x approaches c for f of x to the m constant divided by the n constant, that is still the same as writing the limit as x approaches c for f of x to the m over n. Wait, the whole limit is raised to the power. My apologies. I misspoke. There we go. Okay, so this is the basic rules for limits. The biggest thing to really focus on is this one. This is like your golden rule. A lot of people don't really understand what this means in Calc 1, so it makes it hard for them to understand what it means in Calc 2 as well. And this right here, like, the reason you guys are taught this basic set of rules here is so you can understand that the goal is not to memorize these rules, because these rules are very obviously applicable to many things. Like you could have a bunch of different problems that follow these basic rules, but you need to be practicing them on your own. I'm showing you guys these rules so you understand what the end goal here is, and that is if you have a very complex derivative or integral or mathematics problem, the first thing you should do before starting that problem should be to think about which of these rules is going to apply and how you can separate that problem into smaller problems. Because if you're not thinking like a problem solver, you're going to have a hard time learning calculus. And calculus is all about problem solving, which is why it's the main math for physics. But I am no physicist, so I don't know. I'm not going to go into the physics stuff. I like math the way it is. I don't like adding all the symbols and stuff into it, which, fair enough. I guess proofs is also just nothing but symbols. But I don't know, I just like working calculus problems because I think it gives you, like, there's a lot of math where you can work a problem and it just feels tedious. It doesn't really give you a rewarding feeling. But you'll see with calculus, especially, once you start getting into the harder problems and stuff, you'll kind of get that feeling of accomplishment, like, nice, I can do this. Okay, real quick, just because I don't know who's watching this and I don't know who's gonna need help with what, so like I said, I'm just gonna cover it all. So we've got limit of a polynomial. I think you can all see where this is going. So we'll just say limit as x approaches 4 for the function. What's a short one? Like 2x squared plus 3. So obviously we're just going to plug the 4 in for the x. So that's going to give us 2 times 4 squared, which is 16, plus 3. 2 times 16 is 32, plus 3 is going to give us 35. So as you guys can tell, we have a question. You have a situation involving the use of half-angle formula. Does the entire limit get substituted, or only the part where the half-angle formula is needed? I think I know where you're going with that. Let me double check. Let me draw out an example and you can kind of just tell me if it's right. Just give me a yes or no if this is right. So let me think of an example here. half angle formula. So if we've got the limit as x approaches, I don't know, pi for sine of 2 theta. I'm just using a double angle formula because it's going to be the same situation. It's going to be the same rules. So you could write this as limit as x approaches pi for 2 sine theta times cosine theta. And then you're just going to plug in pi into the thetas. But I think what you're asking is, if you're given a situation like this, where you have 2 sine cosine theta, you're probably wanting to know if you put the constant 2 out here or not. What I'm saying is that if you put the constant 2 out there and then worked it all versus just plugging in the pi directly for the double angle formula, it's going to give you the same answer. So it is a matter of preference at some times, because you don't always have to break it apart. Like I was saying, I think that's what you're asking, because this is a very, like one of those problems where you're going to probably want to dissect it. Like an example for a more complicated version of this would be limit as x approaches pi for, and you're probably going to be given it in this form right here, sine of 2 theta over, I don't know, let's think. We'll just say over cosine theta. So the reason knowing this type of thing would be important in this situation is so you can go like this. We can go, okay, so that's limit as x approaches pi. I know that sine of 2 theta is equal to 2 times sine theta times cosine theta. And now we've got a product on the top and a term on the bottom that we could cancel. So that would give us limit as x approaches pi for 2 sine theta. So I didn't mean to confuse you. I guess really the way you should think about this is that at the end of the day, it's just math. Those limit rules are for the very end of the problem. Like the only time you would use that limit rule is when you put this out here, and then we would get 2 times limit as x approaches pi for sine theta. Because obviously you can't apply a limit to a constant. That's why I was saying that the 2 sine theta is the formula of the double angle, or it's the double angle. Yeah, this is just a double angle. Half angle is a little bit more of a pain in the butt because it's got a lot of radicals in it. This is sine 2 theta, and that's 2 times sine times cosine, which is, these are equivalent. This sine 2 theta is equal to 2 sine cosine. This is just a type of problem I worked out because half angle formulas, you might see 1 or 2 of them, but they're not going to be very common in test-like situations. But a double angle formula, the reason they're not common, by the way, is not because they're impossibly hard or no one uses them. It's because it would be really hard to put that into a type of problem like this, because you're not going to see, I think Calc 1, the main goal for teachers is to give us like a class in which we can really see the beauty of math. Because this stuff right here, like, when you work it out, a teacher likes seeing a good math problem as much as a student does. Like when I write math problems for my students, I love just working problems out that are very complicated but always end nicely. And most professors that I've worked with, if not all of them, are very similar to me in that way. They like working, if you know the concepts, then you'll be good to go. Like the double angle, half angle stuff, you can figure that out, but it's mostly going to be about math and canceling terms and knowing which ones can expand into more terms to cancel. Does that adequately answer your question? Perfect. All right, let's see what we got next. Ooh, I've got some examples. We are at the end of our thing here. No, that's boring and I don't want to do that one. Okay, what else we got? Rate of change. Yeah, this would be something good to explain just real quick in case we have someone in here that like hasn't taken a math class in 4 years. Okay, so calculus, or at least the differentiation part, is based upon the concept of rate of change, which we would denote like this: change in y over change in x is equal to, for this, f of b minus f of a over b minus a, which you guys should remember that pretty clearly. That's from very early high school, if not middle school. It's just, it's like that's how you find the slope of a linear function. So calculus is just like this, but a bunch of times, because you're finding the slope of the slope. Once we get into third derivatives and fourth derivatives, you'll find the nth slope or whatever. But this is what it's all based upon right here. This is the fundamental stepping stone for calculus, because then it gives us this, which is going to be, I went over this last time, the difference quotient, f of x plus h minus f of x all over h. And that's the difference quotient. And if we put it for lim as h approaches 0, then we get a derivative. So next topic we'll go into is continuity, because I said I would cover it. And we're about halfway through our session. Oh, dropped my marker. Yeah. Alrighty, so I'm gonna erase this just because I just wanted to give a rundown. It was the end of the kind of limits thing until we get into infinite limits, which is right after continuity. Oh, I think you guys might even get the squeeze theorem in this one. That one is everyone's favorite and least favorite theorem on the planet, because it's very easy, but you never remember it when you need it, because it's something, this is the only time you'll ever use it right now, and then you'll never see it again unless you're in a math competition, which is where I saw it, and that's why I know that you won't remember it. So we got our constant c here. Let's see. I'm just going to draw out some graphs because I think that's probably the best way to represent continuity. So let's see, this is limit as x approaches c from the left side for the function f of x equals limit as x approaches c from the right side for the function f of x equals f of c. So this is continuous. A closed circle on the line does not make it continuous, just as a point here would not affect its continuity. Continuous, if it's continuous, that means you can draw the line without lifting up your pencil. If there's a hole in it, then unless it is complete, it will be non-continuous. You know what? Here, I'll show you guys an example. Let's see. So for example, you can only have one limit. That's basically what this rule says. You can have one solution to one limit. You can't have an impossible limit that's not going to work, which is what's nice about calculus, because they stay in our realm of existence. So now let's look at one that's not continuous. For instance, if we have some point C here, then we've got this guy, and then this guy. So this right here, let's see. This is going to obviously be undefined for f of c. F of c equals undefined, which means that this is not continuous. And the reason is because these holes mean that this is going here and then continuing here, but at c, there is no limit at c, so it does not exist, which means that this is discontinuous. The quotient rule and the difference quotient are the same thing. No, quotient rule is a division rule. Difference quotient is like a very fundamental thing in calculus. So the quotient rule, you guys haven't even learned this yet, or I don't know, but since we're still on limits, I'm assuming nobody's learned this one yet. So the quotient rule is like this: f prime of x times g of x minus f of x times g prime of x, all divided by g of x squared. And that's how you take the derivative of f of x over g of x. You have not learned this yet. That's what the quotient rule is. The difference quotient is the f of x plus, this is the difference quotient, f of x plus h minus f of x over h. Yeah, no problem. Okay, so now continuity. Let's write out some rules for this concept right here of continuity. So continuity at a number. I'm just going to write out the textbook definition for you all so you have no problems with understanding it. A function is continuous at a number c at a number c if rule number 1, f of c is defined. This is going to be your easiest rule to check, and it should be the first one you check, which is why it's rule number 1. So rule number 2, limit as x approaches c where f of c exists. It's almost like these two are the same rules. 3, limit f of x, shocker, shocker, as x approaches c equals f of c. So basically 3 rules that are all the same. And yeah, that's how you check continuity. This right here, if you can, the most basic go-to test is if you have to lift your pencil when you're drawing it, the limit doesn't exist. But there are some weird situations. Here's a good one. So we've got a graph C, then we've got, this is one of those examples in which you guys might get stumped on it here. Right, so like I said earlier, a plain dot somewhere on the graph doesn't affect the continuity as long as it's filled. But here is where it does affect the continuity. So if we have a dot in between those 2 points, then f of c is defined at that point. So this function is considered continuous. So let's see what else, what other types of continuity we've got. Okay. So as y'all can see, just having that point there, I mean, this is really as complex as continuity is going to get. Like, you're going to see some weird stuff, but if you can follow a basic, the hardest that continuity is going to get to is the interval from some constant number a to some constant number b continuous. And if you can draw a line and figure out when to pick up your pencil and when not to, which is this right here is really going to be your biggest exception that you'll run into. You might find some weird looking ones, but these 3 are the main shapes you'll see with this type of stuff. So, let's do a problem then. Screw it, all right, that'll be fun. Let's do some math. That's what we're here to do. Now we've gone through the basic relapse. Now we've gone through the basic recap. Sorry about that, I misspoke. And now it's time to start doing some math because I'm starting to get a little antsy just sitting on this chair. All right, let's do one with a radical because I know you guys love your radicals. No, that's boring, gosh. Where's a good one? Here, this is kind of good. This is like a little bit tricky. Limit as x approaches c3. From the left side the function x squared minus 9 over x minus 3. Okay, so I want you guys to attempt and solve this one, and just if at least one of you gets the answer, just type done whenever you're ready. This shouldn't be too bad. And the question I want to ask is this continuous or discontinuous? All right, well, sometimes you got to answer your own questions, right? So let's do that. So if we plug in 3, obviously we have to do it from the left side, because if we just plugged in 3 minus 3, that is dividing by 0, and that's not okay in this class. So what we're going to do then is we're going to look at this thing right here and think, okay, let's have a little traumatizing high school flashback and remember our basic rules of functioning. So this is called a difference of two squares. Good job, John. I like you. All right. Limit as x approaches 3 from the left for x plus 3 times x minus 3 divided by x minus 3. Now this is solvable. This is what I was talking about, that basic concept of, breaking down the problem. It's just like math has always been, except now we've got more steps to break down. So we cancel this x minus 3, this x minus 3, so now we get the limit as x approaches 3 from the left side for x plus 3, which is going to give us 6. But we know that f of c does not exist. So even though we got an answer for this, this is still a discontinuous situation, because f of c does not equal 6, because f of c does not exist. Does that look right, John? It's right. Okay, next problem. Let's see what we've got here. One-sided continuity at a number. F is defined by C. Okay, I'll just go over this real quick because this shouldn't be too hard to grasp. Let's see what we got here. Where is my red marker? There's my purple one, that'll do. So this right here is just one-sided continuity. And the way that looks is, I'm gonna make some room here. How do we know f of c does not exist? Okay, I'm glad I caught that, because if we have limit as x approaches 3 for x squared minus 9 over x minus 3, then if we plug this directly in, we would get divided by 3 minus 3, which is equal to divided by 0, which is does not exist. Yes, divide by 0, that's why it doesn't exist, exactly. And that's not always going to be the case. Like, when you guys get to infinite limits and stuff like that, you'll learn about this thing called L'Hopital's rule, which will tell you what to do when you end up getting a divide by 0 or an infinity over infinity or something like that. Because those numbers are not real numbers, but they do exist in the imaginary number field, which very real math happens in the imaginary number field. Okay, so one-sided continuity. So we got limit as x approaches c from the left for the function f of x equals f of c. So I'm just going to draw a hypothetical graph here, what this could look like. If it's approaching it from the left, it's going to come in here. And then if it's continuous, it's going to be close like that. Now the other side would look like this. Limit as x approaches c from the right for f of x equals f of c. And we'd have a graph like this, something like that, which brings us to the next point. If both the right and the left converge at the same number c, then it is continuous. So let's see. Continuity on an interval. Let me see if I have any problems written down for this specifically. Okay, here we go. This will be our first little kind of interesting problem today. I'm saying kind of interesting, not because I don't think that the math you guys are doing is interesting, because I know that it's quite interesting to y'all, but I just because I'm so excited for how interesting the math you guys are about to be doing is going to be. I think a lot of people sleep on calculus, but it is a very, very exciting course. You learn math that a lot of people don't know exists because a lot of people have never taken calculus. So you can think of it as a privilege to learn it. So my question to you now, is this function continuous? On the interval of -2 to +2. Just a simple yes or no will suffice. You guys, I mean, honestly, if you don't know, just feel free to guess. Like, you'll probably get it right. So, continuous, non-continuous, do we have a vote? Okay, we got one yes, one no. So let's look at the graph. All right, so we could view this as, let me think, a square root graph would look something like that, but that's gonna be negative, so it's gonna go that way. It's gonna be +4, so it's gonna be over here. So the graph for this is gonna look something like this. But we're only looking from the interval from 2 to -2. So it is indeed continuous on this interval. By the way, this right here is the difference between making an A or a B or a B or a C or an F in this class. You kind of have to know what a general function shape is going to look like. There's 8 basic function shapes. That's cubic, quadratic, parabola falls into quadratic, linear, step, logarithmic, exponential, etc., etc. There's a bunch of different function shapes, but for this class, you really only need to know a couple of them, which is just going to be your basics. Yeah, so this is indeed continuous. And the way we can prove this mathematically, if you're not a visual learner, is we can look at it like this. So we got the square root of 4 minus x squared. So let's plug in -2 here. -2 squared. So that's going to give us the square root of 4 minus 4 equals 0. Square root of 0 is just 0. That is still a number, so that's why this works, because it's not like you can have the radical of 0. The square root of 0 is 0, right? It's not the same as division, in which 1 over 0 equals does not exist. A lot of people get these two rules confused. I'm going to connect that in because that looks like it says dive. Okay, so these two are very different. This one, fair game. This one, I don't have my red marker, it would have been perfect for that. Wait, oh, watch this I do. This one, bad. So yeah, this is totally fair game. -2 to 2 for the function square root of 4 minus x squared is indeed continuous. If you took a trig class last semester, this is probably pretty I guess, boring for you because you probably already learned this stuff. But if you didn't, then you can think of it on that way. If it exists, it's fair game. If you have to lift your pencil, it's not. If it doesn't exist, it's not. If f of c equals limit as x approaches c for f of x, then it is indeed fair game. So let's see, continuity. It's almost working. Let's see if we got something good here. Polynomial function is continuous for all real numbers. That's actually pretty good to know. So here, I'll write this down. That's a solid rule. I'm glad I found that. Polynomial function is continuous for all real numbers. Okay. What intermediate value theorem? That's another good one. I guess we can just we've been going for almost 50 minutes now, so I'll just write out some theorems and we can call it a day. Does that sound good with everyone? Because I think there's quite a few in here that you guys would like to know. This should definitely be helpful. And now the next one is also something that will be helpful. Universe function, blah, blah, blah. Let f be a function that's continuous from a to b. F of a does not equal f of b if n is any number between f of a and f of b. There's at least one number c that is in the open interval ab for f of c equals n. Yeah, so that's a long one, but I'm still going to write it out just for y'all. So let f be a function, be a continuous function on interval, closed interval ab. Okay, so then if n, which is just some number, is any number between f of a and f of b, then there is at least one number c that is in the open interval ab for f of c equals n. There is a c, is a number c, at least one, for which f of c equals n on the open interval AB. You don't have to memorize this one just quite yet, but you should expect to see this on probably your first test. This is definitely something you don't have to have it memorized for the first test. You'll have to be able to write. Yeah, you know what? No, I'm lying. I'm just going to say it because you guys haven't taken this class, but memorize these two things. This will help you. Yeah, nice, solid. That was easier than telling you not to memorize it. Okay, intermediate value theorem. So graphically what that means is okay, this is such trash. It's not even useful to do this early on, but I guess some of you might want to know it, so I'll show it to you. Okay. A, C, B, F of A, F of B in. So for this graph, F is every value between F of A and F of B. And what that means is that there's at least one number C that is an open interval AB where F of C equals in. But yeah, for this to work, the basic thing you need to know, this is really the main takeaway for this. F of C has to equal in. Okay, so that is all of the time for today's session. Sorry about last time, guys. I've been feeling pretty under the weather recently, and I was planning on doing yesterday's session, but I ended up throwing up, so I was in bed for most of the night. But I'm feeling much better today, so I hope this session helped a lot, and I'm looking forward to seeing you all at Sunday's session, which will be 5 p.m. Thanks for coming, everybody.